Welcome back. In today's lesson, we will delve into the concepts of current and resistance. We will look at the underlying physics, the mathematical relationships, and the practical applications. Let's begin. Electric current, denoted as I, represents the flow of electric charge through the conductor. Formally, it is defined as the rate at which charge Q flows through a cross-sectional area A of a conductor. Mathematically, it is expressed as dq dt. The unit to measure the current is the ampere A, which is 1 coulomb per second. In metallic conductors, current results from the drift of free electrons under the influence of an electric field. Thus, by the random motion of electrons, an applied voltage creates a net drift velocity, Vd, given by I over NAE, where N is the number of electrons and E is the fundamental charge of the electron. Resistance R quantifies how much a material opposes the flow of current. Ohm's law provides the fundamental relationship delta V equals to IR, where delta V is the voltage across the resistor and the resistance is given by. This relationship is derived from the microscopic perspective of electron scattering with a material. The resistance of a material depends on the resistivity ρ, the length L, and the cross-sectional area A, given by R is equals to ρL over A, reflects these dependencies. Ρ is the resistivity of a material and is a specific property that varies with temperature and is crucial for designing circuits with desired electrical characteristics. Several factors influence resistance, including material properties, dimensions, and temperature. For instance, copper has a low resistivity, about 1.68 times 10 to the negative 8, compared to nickel, which is 6.99 times 10 to the negative 8 ohms per meter. The resistivity of a material generally increases with temperature, which can be described by the temperature coefficient of resistance alpha, where ρ of T is ρ0 times 1 plus alpha times T minus T0. This relationship is crucial for high-precision applications and electronic devices, where temperature fluctuations can significantly impact performance. Ohm's law extends beyond simple resistors to more complex circuits, although we will talk more about that in coming lessons. These principles are fundamental in analyzing and designing circuits for specific applications, from simple electronic devices to sophisticated integrated circuits. In practical scenarios, understanding resistance and current is crucial for device reliability and efficiency. For example, in power systems, engineers must ensure that resistive losses are minimized to improve efficiency. Additionally, in semiconductor devices, resistance and current characteristics dictate performance metrics, such as switching speed and power dissipation. There are some engineered materials that exhibit zero electrical resistance below a critical temperature, usually very low. These are the superconductors, and they have surprising properties. This phenomenon, explained by quantum mechanics and the BCS theory, has significant implications in high efficiency, power transmission, and magnetic levitation. To recap, electric current is the flow of charge and resistance is the opposition to this flow. Ohm's law and the dependence of resistance on material properties, dimensions, and temperature are fundamental on both theoretical and applied electrical engineering. Thank you for joining me in this discussion on electric current and resistance. For further exploration, consider diving into specialized topics such as circuit theory, semiconductor physics, and material science. See you in the next lecture, and may science be with you.